Thank you.
So our next talk is an interesting use case with a multi-camera instant replay with slow motion called Futatabi. Please welcome Steinar.
Thank you. So I have two great passions in life, at least at the time. One of them is programming, and the other one is the sport known as ultimate frisbee. And when I tell people, well, frisbee, and they're like, yeah, well, how can you play anything with a frisbee? And I try to explain to them, well, you throw to your teammate, you want to get inside the goal. And they go like, what? And I try to show them a video. The problem is when I moved back to Norway, where I live now, and started playing tournaments, the stream basically looked like this. And it's pretty much impossible to see anything, right? You can see sort of the players, but there's supposed to be a goal line here, and good luck seeing anything, but it's supposed to be around here somewhere, but it's all smudged out. It ran on Windows, on XSplit. They managed to get a full like 15 FPS sometimes. The Virus scanner would take 1 core. And it's really, really hard to explain a sport to someone when you can't even see are they in or out, when the point is to throw inside the zone. So we thought, can we do better than this with free software? And it's not an obvious answer. I've never heard of sports production being done by free software before. We thought, okay, we'll give it a shot. And this is Nageru, my live video mixer, which I presented here actually in this very room 3 years ago. It's grown a lot since then. So if you tried 1.0 3 years ago, maybe give it a shot now. There's a lot of new features. So I'm going to do a very quick rundown first of what our stream is looking like. This is a standard ultimate field, indoors, 40 by 20. I play in handball fields in Norway. In all of the countries, it's outside. You can see there's not a lot of room, so we are pretty cramped where you can put our cameras. First of all, we have camera 1. Camera 1 is your standard wide angle, let's look at the entire field thing that you will see from any normal sports thing. We're trying to be very sparse on manpower, so camera 1 there is run by the producer. He's tilting it with his left hand. He's operating Nageru with his right hand. He's also doing audio mixer. He's also doing graphics. It's a fairly busy position, but it's a lot of fun. There's also camera 2. Camera 2 is a detail cam, right? It just basically follows the guy with a disc. It's a bit more zoomed in. It's nice for these detail shots. And most of the time, I think maybe 85% of the time you want to be in camera 1. Maybe 10% of the time you want to be in camera 2. And then we have 3 and 4. And 3 and 4 are what we call beauty shots. They're GoPros actually perched high above each of the 2 goal zones. So you can see the end zone more or less. It would be nice to have them even wider, actually. GoPros are low power enough that we can actually just run them on power banks. We don't run power to these. We just put up a power bank, put them on a very, very cheap and high extender, and then we run SDI converter and GoPro on these power banks that last maybe like 18 hours. And now if this sounds like a lot of equipment, maybe it is, but almost all of this is either bought secondhand on eBay or borrowed or otherwise. So it's not an expensive production by any means, at least not compared to traditional broadcast. So after all of this, it looks basically like this. You can actually now see the goal line. It's up here. There's HTML5 graphics here. This is embedded Chromium. And was it in or out? Who knows? Right? 70,000 lines of code later, and I still don't know whether I'm in or out. For the record, I was in. We looked at it later, but it became clearly painfully obvious that we needed some form of instant replay. We wanted to be able to see shots again. We wanted to be able to see shots from a different angle, like camera 2 instead of camera 1 or legs, and we wanted to be able to see it in slow motion. So we went online and looked, okay, well, we need a box to do this. What can you get? This is the EVX XT3. This is pretty much the standard thing in broadcast. If you look at any major sports event, they will either have an XT3 or they will have many of them. Unfortunately, as you can see here, the price is £99,000, and this is a bargain. You also need to pay $30 in shipping. Maybe you can get that waived. And to make it even worse, right, the seller is currently on vacation, so you can't even buy it. Now, there are cheaper options, but they're all generally in the €10,000 range. And that is essentially like a Windows box with some software and a video card. So we thought, okay, let's try making our own. And this is, of course, where Futatabi comes into the action. The first U is silent because it's a Japanese word. Basically, we try to get all the frames from all the cameras from Nageru over IP. We store them, and we want to play them back. When you do this, you have a frame server. Now, there are a few problems, of course. Uncompressed video, we just talked about it on 10 gig. It's fairly voluminous. You can maybe do it over the network, but storing it, and when you want to store all of it, say you want to store 12 hours of uncompressed video, it's not going to fly. So we are doing MJPEG compression. You would think, OK, well, why do you want JPEG? JPEG is like an 80s format. But it's very, very performant, and it's actually pretty good. In fact, on recent CPUs from skylighting up, you actually have a hardware JPEG encoder. So instead of using 4 cores to do DVC Pro or whatever, you can just send it directly through the Intel GPU, send it over the network, store it here, and then you have some sort of UI, which we'll be looking at later, to pick out, for instance, this segment here, and play it back. And even when you play back these unmodified frames, you can just echo the MJPEG back. You don't even need to decode or re-encode. So you get maximum quality. You don't get any sort of CPU usage. But we also wanted slow motion. And that begs the question, well, we have the unmodified frames here. We want to slow down by 2x. But what do we do with these ones in the middle? Now, the obvious first choice, of course, is just to repeat frames. Repeat them twice, 3 times, 4 times, how many times we need to slow down. And that looks like this. It's very, very choppy. And it's not really something you want to show to people. Now, I will say, though, that I've deliberately picked a very, very hard sample. There's 2 reasons for this. A, it's a lot more fun to reason about the things that go wrong than the things that go right. I mean, the easy case is who cares, right? The other one is that when you're having a talk like this, these effects can be really subtle. It can be very hard to see things when they're just flying by once. So I want to exaggerate a bit. Now I'm playing this. It's a lot of motion. We're doing 4x slowdown instead of 2x slowdown, this kind of thing. So it's just to make things clearer. So OK, so repeating frames is maybe not the best. What about fading frames? It's not really a lot better, right? It's still pretty choppy. So we need to do something even better than this. I have taken 2 neighboring frames and overlaid them. So you can see sort of we have a frame A, we have a frame B, and we want to find something in the middle. And obviously what happened in this frame, like say you have this here. On the first one, you have this here. It moved a bit. His leg here moved a bit from the right to the left, and so on. So somehow these intermediate frames in the middle, or 20% between, or 80% between, and what have you, it has to do somehow with motion, right? If we can estimate the motion like this, maybe we can try to synthesize in between frames. So this brings us to the idea of optical flow. Optical flow is basically a model that says, well, all pixels came from somewhere. Here we have made an estimate. Again, it's what you'll see first of all, of course, is all these little arrows pointing up and to the right, and that's because the camera moved down and to the left in between these frames. But it's also picked up that the disk here is moving to the right, sort of. It's picked up that the player is moving to the left. There's slightly different arrows here, and so on. So if we can take these arrows, like our flow field, and somehow invert and halve it, which is much harder than it looks like, then we can maybe get an idea for not where did the pixel go, which is not that useful, but more where do we want to sample it from. So this part is actually non-trivial, but we're not going to talk about it. We're just going to talk about estimating the flow field instead, which is a very difficult problem in its own right. There are more than 200 papers dealing with optical flow. I read maybe like 20, 30 of them. There are these rating lists. There's new papers coming out really every week. But between the time where there are these rating lists for like who can make the best flow with the best algorithm on standardized tests. And between me writing this talk and now, I think like the top list has changed 3 times or something. But most people don't care about real time. We need to be able to synthesize these in-between frames basically 60 times a second, or at least 30 times a second if we can keep every other original frame. So this paper here caught my eye. It's from 2016, and it says the magical words 300 to 600 hertz, or frames per second. Now, of course, it isn't really 300 frames per second. It's more like 10, because they exclude a lot of preprocessing. They run in low resolution. And of course, their numbers there are on the lowest quality presets, which isn't really good. But I thought, OK, maybe I can use it. They have reference code. It's sort of unclearly licensed. It says GPL3 in some places. It says for personal use only other places. So I ended up re-implementing it, not the least because I wanted it on the GPU. My hope was that, well, okay, if they can do 10 hertz on the CPU, maybe I can do like 60 hertz on the GPU. Let's try. I'm going to go give a very, very, very high-level overview of how this algorithm works. If you want the full details, you can probably read the paper, but it's fairly dense. So we start off with a motion search. We start on low resolution, as you might see. We split the image into multiple overlapping 12 by 12 pixel blocks, and then we go look in the other picture. Can we find something that looks like it? We start here in the middle, as you can see, like the bluish square, and then we have these squares here that show the algorithm consecutively homing in. Now, if you do video compression, you'll already know motion search, but this is motion search with a different goal. This is not motion search for just finding the most efficient motion vector. This is for finding real motion. And we also care a lot about the subpixel precision. We don't want to stop at like half pixel or quarter pixel. So this is a gradient descent search. We start at 0, and then we try to figure out, okay, which direction am I going? And eventually, hopefully, converge. This works fine as long as we don't need to have motion that spans like many, many pixels. In this case, it's 1.5 pixel because we reduced the resolution. So after this, we have, oh, by the way, I'm not colored blue for a reason, because when we have a million arrows, it's very hard to see which way are they all pointing. So instead of coding them as arrows, we use a fairly standard representation where the hue is which direction it's going, which is the angle, and the lightness is how strong is it. So that gives us now a bunch of little squares. This is a sparse flow field for each and every motion block, and they're overlapping. First of all, we need to get up to the resolution of the image, or at least this level. So we do a process called densification, where we blend between all of these motion vectors or hypotheses based on how good were they for the single pixel. Right now, it looks sort of messy. So we have a separate step called variational refinement, which is, unfortunately, I don't have time to talk about this. It's like 2 hours. But essentially, it sets up a huge nonlinear differential equation, which we solve on the GPU numerically. It's not as smooth. It does some sort of edge preserving smoothing, but it does a lot of other things. At this point, we have a flow field. We could have scaled it up and used it for our algorithm, but instead, we now go to the next resolution. We now use the double resolution, and we use this flow field here as input for the motion search algorithm. So again, remember I said the motion search works well when it only has to move a little. Well, now it has to move only a little because it already had a pretty good estimate. So this is our new motion search, our new densification, our new variational refinement. We go one step up in resolution again, motion search, and now you can see things like the disk is starting to show here. The people are in the background. Densification, variational refinement. All in all, this is about 200 passes on the GPU. It really gets a lot to do, but it loves parallel work. And of course, you can see it's not perfect. So how good is it? And for this, we have standardized benchmarks, thankfully. This is the MPI Sintel benchmarks. I think a lot of you will know the Sintel movie from the Blender Foundation. Someone's re-rendered it with motion, with optical flow data. So this is our ground truth. Since it's a render, we know exactly where every pixel is going. And these are our estimates on 4 different quality levels. You have like quality level 1, 2, 3, and 4 from the paper. They vary in like what resolution do we stop on, how many motion search iterations are we running, all this kind of thing. And you see as we're getting down here, we have this EPE, which is the endpoint error, which is how much did the flow miss compared to the reference. It's going down, at least until we reach like quality 3, quality 4 here. And then, of course, it takes longer and longer. Now, these times here, I'm quoting 6 milliseconds on RTX 270. This is estimating forward flow from A to B, estimating backward flow from B to A, computing the in-between flow, like the halfway flow between them, and doing the actual interpolation. So even at 1080p, we're at like 12.9 milliseconds, and that's under our 60 millisecond target. Compared to the CPU implementation, it's more than an order of magnitude faster. Depends a bit on your settings in your GPU, of course, and it's a few % better in terms of endpoint error. Now, you can see it's still not perfect. It's still far from perfect, but does it matter? So we can now try taking just these 2 frames up here and see and just interpolate very, very smoothly between them. And the result looks like this. These are just 2 frames. Let's just look at it again. You can see there are some issues. In here, for instance, you can see it has problems with occlusion, but it did get the mirror, get the sword right. The background motion here is hardly even visible. And remember, this is like 50x slowdowns. This is fairly good. Let's look at the original example again now with this algorithm. It's not so bad, right? There are some artifacts, especially if you know what to look for. But again, this is a hard sample. It's time for the demo effect. And I'm going to try to show the UI as best as I can. Now, of course, my laptop isn't really fast enough for this because it doesn't have a nice GPU, but I took some test data in low resolution. You can see here, this is real data. I'm giving out, as part of this, 12 hours of real multi-camera data because it turns out it's really, really hard to find online actual multi-camera data. So the way this works, we have, I've been moving around, some buttons around, by the way, for the demo, just because it's hard to see anything at the bottom. So we have a clip list. Normally, I would use the keyboard for this, but since it's easier to see what's happening with the mouse, I can click Q in. And when I'm happy, when they've been doing something interesting, I can press Q out. Now I have a clip. This is just an instant in time. I can preview it up here. Maybe I want to have camera 2. OK, maybe I wasn't completely happy about the start, so I can scroll it here. If I want to, I have this little DJ controller here, which is much, much nicer to work with. It's basically super cheap. I think this is like €100. If you want to buy a professional remote, it's something like 1,000, 2,000 euros. And once I have my clips, I can queue them up. Maybe queue it from both cameras. And now I can play it back. OK, maybe first wasn't so interesting, but it will fade nicely over to the second one. At least once it's done, it was sort of long. I can edit these while I'm running if I feel it's... Yeah, so it will play it out on TCP socket. Will go nicely back, hopefully in reasonably high quality. If you want to be really fancy, you can turn off the speed lock here. And you can pull this little slider to ramp it down to very low speed. Let me just play it again. Here, and this, ooh, very dramatic. So I guess that's basically the demo. We have like media control over these things here. We have, of course, undo. There's a full manual if you want to go look at it. So that's basically it. Now, while I'm taking questions, I think maybe I have 5 minutes for questions. I'm just going to play here some real world. This is actual stuff from the last event we did. So this is an actual replay or replay operator doing actual mistakes in real time. So this is pretty much what you can expect in 2x. So any questions? Yes. Wait for the microphone, please. Oh, they have to change batteries.
Was the output of the application a separate SDI, or is it a stream? Or
so I don't think the microphone is working, but I'll just repeat it. If the output is SDI, no, the output is a stream. It's a standard HTTP stream in a Matroska container, echoing back frames. Half of them are the MJPEG originals. I try very hard to sort of lock into the original frames when I can, and half of them are these synthesized frames. I would probably add SDI output if I needed it. It's not hard to do. But generally, the entire idea is that you have this Nageru and you have a separate Futatabi operator, and it just goes in there anyway. So why would I want SDI? But it's most certainly doable.
Hi. Do you happen to have an API for the image interpolation?
It's a class. It's a C++ class. It's fairly well contained. You give it 2 raw frames, and it gives you back another frame, well, in form of texture on the GPU. So it's certainly reusable. It's GPL3.
Mm-hmm. Would a readback kill it?
I'm doing readback. I'm doing readback for the JPEG.
Right.
But I'm doing asynchronous readback, which is, of course, important when you're doing GPU.
Mm-hmm.
But it's certainly possible.
OK, cool. Might ask you about it.
other questions? Yep.
Did you have to do anything special for camera synchronization between the 4 cameras, or are you just ingesting 4 SDI feeds and?
I'm just running 4 SDI feeds now. This is a low budget thing, like I said, and we don't have any clock synchronization because the clock synchronizer would be like a master clock would be like 500 euros anyway, and our cameras are HDMI in the first place. We just convert into SDI. So we are doing some, and Magero has internal frame queues for all 4 cameras. It's trying fairly hard to keep these queues low, or to keep them short, as much as it can without risking too much frame drop. So essentially, they're like a frame or 2 or 3 from each other. It's not perfect, but it's I don't see any.
That's good enough.
I can't see any visible difference between them.
Thank you.
Other questions? Yes.
The previous talk was about GPU optimization, and since in OpenCV, I think there is a modular function to perform GPU optimized optical flow.
I think it's actually the same algorithm.
Oh, okay.
But I didn't think it was GPU optimized.
I think there is one, but it may be in the country. But
Okay, maybe I haven't actually looked
Not sure.
in OpenCV per se.
okay, and I was wondering how does it compare to?
Yeah, no, I don't. I mean, the problem is, of course, again, every week there's something new. If I had this talk in 5 years, I'm fairly certain I would stand here and talk about neural networks. It's coming full speed now. I think everything state-of-the-art quality-wise is approaching neural networks. But it's still, I mean, the best things are 150 milliseconds, and that's just too much for me. So I just had to pick something, right? Eventually, in a future version, maybe I'll be switching. I don't know. I'm not bound to this specific algorithm, even though I used literally a month to decode the variational refinement in the paper with all the strange tensor notation and typos and stuff.
Thank you.
Hey, nice talk, thanks. You mentioned some artifacts that appear in the frame interpolation. I just want to ask if you could describe some of those, and if any of those artifacts are located at the edge of the frame.
I love that you didn't see them, because they're playing now and there should be artifacts everywhere, right? Generally, edges are not a big problem. The really hard part is occlusion. When you have an object that moves right and the background is moving left or the other way around, and the optical flow assumption really breaks down because, well, things didn't come from, it always assumes things move from A to B. But if it just came from behind something, it didn't come from anywhere, so it really breaks down. Motion blur, any kind of blur will also give you a problem because now your pixel doesn't go one place because half of the pixel is the background, half of the pixel is the foreground, and they're moving different ways. I think if I go all the way back here, you can maybe see some of these issues, but except that I don't think going backwards in OpenOffice is with video is very easy. I think maybe, yeah. If you look at when he's moving his arm very vertically down. So look for the place where he does like basically this, and that's where you see it. It sort of gets broken up. But again, this is 4x. In 2x, it's very hard to see. But I was also surprised that edges don't actually matter. Unlike the original paper, I don't pad with black. I pad with the edge, because that's what the natural thing for the GPU is, and maybe that helps a bit.
Thanks.
We have
Question.
1 more minute for questions. If it's anything.
Yeah. 2 minutes, even. Yeah.
Really impressive. For you, is this the end? Is it good enough? Or do you want to look at the newer papers for this? Or are there other things you want to build into this software next?
First of all, I want to use it even more than we've already been doing. Certainly, I'm open to adding new and more fancy algorithms. I doubt I'll be, I mean, I used to every week just reload this Middlebury rating list over and over again. I don't think I'll be doing that because it takes a lot of time. I think basically there will be features. There's a lot of things that I want to do, and especially in terms of media control, in terms of UI. I want to be able to support more of these X3 workflows. For instance, I mean, a lot of slow motion is very bound to how an EVXS works, but it's a very efficient workflow, and everything needs to go by the second. So every time I can shave off like half a second of the UI by making something simpler, that's really the way I want to go. For instance, I did queue in and queue out. I talked to slow motion operator the other day. He said, well, they never do queue out. They just set queue in, start playing, and then just abort it manually, because then you don't need to wait for the clip to happen. So I think maybe in the UI department is first of all. But yeah, I would love to have users and see their feedback. Also, by the way, read the manual. I've spent a fair amount of time trying to explain how the slow-mo work from an operator's point. How do you want to work with the producer? This kind of thing.
Last question? No?
No, I think there's nothing. Okay,
Thank
thank
you,
you.
Steiner.